Hello students, we are going to look at chapter 11 on alkenes. Alkenes will be relatively different from alkenes because for alkenes, if you remember, it contains all single bonds, okay, or CC single bonds or CH single bonds, and these bonds are relatively strong, which make them non-polar. So in order to force it to react, you need a very reactive species such as a radical. So that's why for alkenes, you learn about free radical substitution towards the end, and that probably remains as the major reactions for alkenes you're going to learn in H2. However, for alkenes, due to the presence of the CC double bond, with the presence of a pi bond, which is relatively weak as compared to the sigma bond, there will be a lot more reactions to deal with, and we are going to discuss them in a while's time. So if you look at learning objective 11.3e, so there will be quite a number of reactions that you need to be familiar with for alkenes. So they are sort of listed down here. And you know that the name of the reaction given is actually electrophilic addition. And for 11.3f, you're supposed to describe the reaction of electrophilic addition in alkenes. And to be more specific, you need to illustrate the mechanism. Okay, and then you're supposed to use bromine as an example. But bromine is just a benchmark, which you are required to learn for H2. But as you learn more, you realize that for assessment purposes and to link up to some other topics, there will be more kind of reagents that you need to deal with for electrophilic addition. So bromine is not the only reagents you need to deal with. Okay. 11.3g is actually on Markovnikov's rule. Markovnikov is actually a Russian chemist which worked really hard in the past to come up with some rules for electrophilic addition and how when HX is being added across asymmetrical alkenes, it gives rise to different products. Yep. So when he came out with the rules back then, he isn't worried. He's not aware of the stability of carbocations. So the rules which he formulated did not actually go into details regarding reactivities. Yep. So as of now, we are aware that the Markovnikov's rule, why did he observe the HX being added in a certain way, is largely due to the fact that the intermediate produced, which is the carbocation, the more stable one will be formed, and the less stable one will not be favored, and that explains why certain products are favored. Yeah, so later we're going to touch on them. Okay, so without further ado, we're going to go into the introduction. So we'll not spend too much time here because basically alkenes, any compounds with a CC double bond, you can call it an alkene. Okay, so common alkenes will be what you have in cholesterol because you have a CC double bond over here, and beta carotene is the orange pigment present in carrots. Okay, so they are characterized by the presence of CC double bond. It can be isolated like that in cholesterol, alpha pinene or ethene, or it could be conjugated. Okay, so conjugated pi system is similar to what you observe in beta carotene. You can see that the alkene here, there's a double bond, single, double, single, double, single, double. So the alternating double, single, double bonds, right, is what we call a conjugated system. So it will be good if you can understand what does this term mean, conjugated. So basically, for conjugated system, they are just separated by a sigma bond. Why is it called conjugated? Okay, so for a very simple reason, I think we have briefly discussed this in the earlier chapter, butyl 1,3-diene, right? The reason why you can get a conjugated system is because if I have a unique alkene over here, which have a pi overlap, and I have another alkene separated by a single bond next to it, there is the possibility of the purple pi system to be parallel with that of the green pi system. So when that happens, the system actually results in a continuous overlap. So this continuous overlap, we say that the pi system or the pi electron cloud is delocalized. Okay, yeah. Another way to describe such delocalized system, we can say that it is conjugated. So conjugated system generally means that when you look into a molecule, you can identify alternating double single bonds. Okay, so that will help you a little bit. And as to why they give rise to special property, etc., I'll leave it. I'll leave you to explore it on your own as time goes by. So let's not bother ourselves with too much detail. Okay, similar to alkenes, the nomenclature would be relatively straightforward, except that you don't have a single carbon member for obvious reason, because minimally you need two carbon to form a CC double bond. Okay, so we begin with ethene. So the starting prefix is still the same, which is F, followed by props, followed by but. Okay, yep. So I don't think there's any huge differences, except that instead of ending with A and E, for alkenes it ends with E and E. Okay, so for 3 member we call it propene, and for 4 member we call it butene. Okay, the reason why for butene you need a 1 over there, right? It's really to indicate the presence of the double bond. Okay, whether is it between carbon 1, carbon 2, or carbon 2 and carbon 3. So usually we number it based on the lower carbon member. So in this case, if you look at this particular butene, right, I number from left to right 1, 2, 3, 4. So the CC double bond is between carbon 1 and 2, so we call it but1-ene. Okay, you can also call it 1-butene. It is not a problem at all. So some textbook or website you come across, it may have name it as 1-butene or 2-butene. Yeah, but for the purpose of H2, we tend to put the numbering in between the prefix and the functional group. So we just call it but1-ene. Okay, so for but2-ene, as the name implies, it will be between carbon 2 and 3. So if you have an butene like this, carbon 1, 2, 3, 4. So the CC double bond will be formed between carbon 2 and 3. And you realize from your earlier chapter on isomerism that for but2-ene, it is possible for it to exhibit cis-trans isomerism. Yeah, because in our case here, the one I'm drawing actually takes on a trans configuration. Yeah, because the H is opposite each other. So for but2-ene, you can have trans but2-ene or you can have cis but2-ene. Okay, so this is where the H is on the same side. Okay, and then okay, so the IUPAC naming, I'll just leave you to read. A lot of details involved. I don't want to go into details, as you probably aware that I'm not too keen in discussing naming, because when the time comes, then I think the naming will come quite naturally if you are familiar with chemistry. Yeah, but maybe another thing I thought is worth mentioning is maybe point number 4. If I have more than one double bond present, it is important to indicate not only the position and also the number of double bond. Yeah, so double bond, CC double bond, as you are aware, is represented with ene, E and E. Yeah, so I'm just going to highlight the ene here. Okay, so if you have 2 double bond, we'll call it diene, 3 will be triene, and 4 will be tetraene. Okay, so maybe just to name this. Okay, why is it called 5,7 dimethyl octa 1,3 triene, right? Basically, the main thing you need to do, maybe I should just draw it out somewhere so that it's actually easier for us to understand what exactly is going on. Okay, so I'm going to draw it out using the skeletal formula. Okay, so like this. Okay, and then 1 up here, and then down up, and then down up. Okay, so I'm going to number the carbon from left to right. So it will be 1. Okay, in this case, I'm going to number it from right to left, because remember, the functional group here is actually alkene. Yeah, so if you want to indicate the presence of the double bond, it has to start from the lowest numbering. Okay, so instead of left to right, I'm going to number it from right to left. So 1, 2, 3, 4, 5, 6, 7, 8. Yep. So in this case, the presence of the double bond is between carbon 1, 2, carbon 3, 4, and carbon 7, 8. So we'll name them based on the smallest number. So in this case, it will be 1, 3, 7. Okay. Oh, sorry, not 1, 3, 7. 1, 3, 6 over here. Yeah. So that's why you'll see this as 1, 3, 6 triene. Okay. And because there's a total of 8 carbon, yeah, so this compound is an octa-triene. So in this case, we need to indicate the presence of the double bond. So that will be octa 1, 3, 6 triene. Then after that, we need to indicate the presence of the methyl group, which is the substituent. So the methyl group is being substituted in the 5th position and the 7th position. And that is why it's being named as 5,7-dimethyl octa 1, 3, 6 triene. Yeah, so that's quite a mouthful, but yeah, that's the way it's being named. So you can just go through the list on your own, and then it might be easier for you to navigate around. And then for stereochemical descriptors such as cis and trans, you will need it as and when there appears to be a CC double bond where cis and trans can exist. So if there's only one potential position for cis and trans and is unambiguous, we'll just call it trans, cis, and then trans respectively. But let's say there are more than 2 positions, that is going to get a little bit more complicated. And if you recall from your earlier in-class exercise, normally we call it something like cis, cis, blah, blah, and then trans, cis, cis, trans, and then trans, trans, something like that. Yeah, so I don't think, I mean, more complicated question like that will ever be given to you, because remember, the purpose of H2 is not about naming, but it's really about you applying what you learn in the reactions, and of course illustrating the mechanism and how are you going to use the basic reactions for structural elucidation. I think those are more important purposes. For cycloalkenes, they are being named in a similar fashion, except that I think similar to what we have earlier on, we always start from the main alkene functional group. So in this case, if we were to number it, we don't do it like 1, 2, 3, 4, 5, 6. Because if we do it this way, it will be called 6-methyl cyclohexene, and that sounds actually a little bit weird. So in that case, we'll number it from 1, 2, 3. So we'll call it 3-methyl cyclohexene to make it unambiguous. Okay, for this particular compound, cyclohexane-1,4-diene, again, unambiguously 1, 2, 3, 4. So the lowest number will be 1 and 4. So we call this particular compound cyclohexane-1,4-diene. Okay, and this particular compound 3,5-dimethyl cyclopentene. So again, it's the same thing we're going to do. So 1, 2, 3. So 3rd position, there's a methyl group, and then 5th position, there's another methyl group. So we'll call it 3,5-dimethyl cyclopentene. Okay, yep. Right, so for exercise 1.1, we are going to draw the structural formulae of these 2 compounds. So let's try to do it. Okay, so for 2,3-dimethyl octa 1, 3, 6 triene. So again, the easiest way is to look at the parent. Okay, so in this case, the parent is octa. So octa means there are 8 carbon in total, and it's a triene, which means there must be 3 CC double bond. Okay, so I'm just going to draw a skeletal structure out first. So just going to use the pen, and then okay. So 2, 3, 4, 5, 6, 7, 8. So to make things easy, I'm going to number it 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then at the 1st position, okay, 4th position, and 6th position, there will be a CC double bond. And then 2nd position, there's a methyl group. Okay, so 2nd position, there's a methyl group. I'm just going to draw it up. 3rd position, there's also another methyl group. Okay, yeah. So this particular compound in this case will be named as 2,3-dimethyl octa 1,4,6 triene. Of course, there is a chiral center, so I'm aware. Okay, so there's a chiral center over here, and of course, potentially 4, 5, and 6, 7 can form cis-trans isomers. Yeah, so again, when we are doing the naming in this case, right, we are not concerned with the stereochemistry. Yeah, the reason why we are not concerned with the stereochemistry is because there is no indication in the naming what should the stereochemistry of the compound be. Yeah, so we just draw one of the stereoisomers. I think that will be fine, and to keep it unambiguous. Okay, and then for B, we're going to have 2 ethyl, 3 methyl, cyclohepta, 1 4 diene. So again, I'm going to highlight the parent. So the parent is actually cyclohepta diene. So the diene is actually at the 1 4 position. So I'm going to draw out the 7-membered ring. Okay, so 7-membered ring is drawn like this. Okay. Okay, I'm just going to randomly number it. Okay, so I'm going to start from here. So 1, 2, 3, 4, 5, 6, 7. Okay, and then I'm going to indicate the presence of the double bond. So that's between carbon 1 and 2. Okay, and then carbon 4 and 5. Okay, like this. And then second carbon position, I have an ethyl group. So I'm going to branch out with an ethyl group like this. And then third carbon position, I'm going to have a methyl group. So again, you might be aware that there is actually a chiral center here. So we are not concerned with the stereochemical naming at this point in time. Okay, yeah. Another thing, since I'm drawing the cycloheptane, right? I thought I just want to illustrate to you a simple way of drawing a 7-membered ring, maybe a 6-membered ring, and a 5-membered ring, okay? Because some of you might have a bit difficulty given that this is the first time you're looking at such thing. I think 6-membered ring is quite easy for most of you. Basically, you're just drawing a hexagon. So to draw a hexagon, right, I think first we draw the rooftop, which is what we call the apex or the inverted V, and then we just draw the 2 lines down, okay? Sorry, it's not so easy to draw using the screen, okay? So, and then after that, I'll draw a V over here. So this is a hexagon. Okay, or you can either draw it like that, or you can draw it rotate 30 degrees. Okay, you can draw it like this as well if you feel like it. Yeah, but this will be more common. It really depends on what you're looking at. Okay, yeah. Then what about a pentagon? Okay, so a pentagon, usually students do not have problem drawing a pentagon. So you can keep the top the same. And then for the bottom, right, you tilt it a little bit to the right or and to the left. So like this, and then you close up. So that's a pentagon. Okay, so remember you tilt this part a little bit to the left and this part a little bit to the right. And then you will seal it off with the 2 carbon. Okay, so for a 7-membered ring, right, you actually do the same, but you will tilt this a bit to the left and this a bit to the right. Okay, so I'm going to illustrate to you below. So the top is the same. So here I will tilt a little bit to the left, a little bit to the right. And then for the bottom, right, what I'm going to do is I'm going to draw it like the hexagon, but I'm not going to connect them. Okay, so I will leave a little bit of space to connect them using a straight line. Okay, so it's like this. Yeah, so this is the way to draw a 7-membered ring. Okay, 8-membered ring, I think most of us know how to draw because it's relatively straightforward. It's actually an octagon. Okay, like this. Yeah. Okay, yeah. So I'm going to move on. Okay, so the electronic structure for ethene, I think the main idea is the presence of the CC double bond. And I think you heard me mentioning that the weakest link is actually the pi system. Because in this case, the pi system will be the nearest, and it's actually on the surface of the molecule. And if it were to react, it will be the first to actually attack the electrophile or any electron deficient sites for that matter. Okay, so because you learn about hybridization, right, and if you heard me earlier on in the isomerism lecture, there is an important need, and there's a real need for you to draw an alkene in a trigonal planar fashion. Yeah, so when you draw an alkene, right, you have to make sure that the bond angle is 120 degrees. So let's say I'm drawing cis build 2 in. So it has to be illustrated in this particular manner. Okay, of course we are not so strict. I think in most cases, the strict parts will only comes in when you are asked to illustrate cis-trans isomerism. Yeah, other than that, actually it doesn't really matter. But you notice that whenever we draw it in zigzag, right, it is already in the trigonal planar geometry. Okay, so for example, like this. And that is also the reason why skeletal structure is drawn in a zigzag fashion, because it's able to showcase the geometry in a proper manner. Okay, and then of course you're aware that cis-trans isomerism exists in alkene, and we have discussed it quite extensively. Yeah, so in order for an alkene to move, I mean to be transformed from cis to the trans isomer, right, there is a need for the pi bond to be broken or to be overcome. It could be overcome through various means. It could be either overcome by heat, which can be quite rare unless the system is heated to very high temperature, but sometimes heating alone will actually cause it to undergo other kinds of reactions. So normally heat itself is not the real solution. Okay, or you can actually use UV light, okay, allow it to undergo electronic transition, which is something you're going to learn in university known as photochemistry. Okay, or you can simply maybe add in momentarily an electrophile and then remove it. Okay, which I think we can cover it along the way lah. Yeah, I don't think we need to discuss it right now. Yeah, so once the pi bond is being broken, you notice that the sigma is not broken. Okay, so only the pi bond is broken, and there will be free bond rotation. Yeah, because remember that for alkanes, all the CC single bonds, if it's a straight chain alkene, right, it can undergo unobstructed free bond rotation. So the free bond rotation will give it the flexibility to take on different conformation. But for an alkene, it is not possible because of the CC double bond. So it will lock it up in a certain configuration. So in order for you to transform from cis to trans isomers, right, there is a need to overcome the pi bond, and in order to overcome the pi bond, something must happen, which I mentioned earlier on. Either you use UV lights or you add a reactant in to cause it to be overcome momentarily, and then bond rotation will then take place. Okay, via the CC single bonds. Yep. Okay, so cis-trans isomerism, I think we have discussed in the isomerism lecture. We won't go into it again. Yeah, but remember that one important condition is that the CC double bond, right? In order for you to exhibit cis-trans isomerism, the sp2 hybridized carbon cannot have identical groups. Yeah, so in the case of 2-methyl propene, I have a CH3 over here. Yeah, and a H which is similar. So even if the other side, let's say I have a Cl and then a Br, even though these two are not similar, right? As long as one of the sp2 hybridized carbon have the same group, then cis-trans isomerism will not be able to exist. Yeah, because there is no difference between this particular compound and let's say this particular compound. Okay, so Br and then Cl. Yeah, because I can interconvert them by just flipping into the plane 180 degrees. Okay, cycloalkene, as we mentioned, up to 7 carbon, it only exists as a cis isomer. I think I kind of mentioned it in the earlier lecture. Yeah, for you to have or for cis-trans isomerism to be possible, 8-member ring and above is necessary. Okay, yeah, so for exercise 1.2, supposed to draw the cis-trans isomer of this particular compound. So again, I'm going to draw it out. So we have a H here, we have a carbon, and then a Cl, and then a double bond, and then a CH3, and then a Br. Okay, you realize that the 4 groups are all different. Yeah, so in our case here, from what you have learned in H2, you are not able to name these two compounds, which means you cannot name them as cis or trans, because cis or trans here means that either the same group, usually is hydrogen, on the same side or they are on opposite side. But in our case here, there is no difference between the groups because they are all different in that sense. Yeah, but if you move on to let's say you learn about H3, because H3 you learn about easy convention, then you are able to differentiate between the two. Yeah, so just a little bit of extension if you wish to know how to name them. For the easy convention, we give a priority, okay, to the different atoms. Okay, so in this case, how do we prioritize them? We look at their atomic number. Yeah, so between H and Cl, H has a smaller atomic number than Cl. So in that case, we will assign Cl a higher priority. And between Br and carbon, okay, Br has a larger atomic number, so we will assign Br with a higher priority. Yeah, so the two higher priority groups on the same site, yeah, for the easy convention, we call this Z. Okay, for the other one, therefore it will be called E because the higher priority groups are on opposite sides. Yeah, so you can view Z configuration as cis-like because the so-called higher priority group are on the same side, but it is incorrect to call it cis. Okay, you probably will just want to call it cis-like, but it's not cis, and this is trans-like. Okay, yeah, I hope that explains it all. And another important thing I need to really highlight to you is that you need to draw them showing the 120 degrees bond angle, which means the bond angle for an sp2 hybridized carbon. Okay, it is of utmost importance when you want to showcase cis-trans isomerism. Okay. Okay, next we're going to move on to physical property. Yeah, so similar to alkenes, the physical property is related to the strength of the intermolecular forces of attraction between the molecules. So in this case, because they are all non-polar, yeah, you expect dispersion forces to exist between the molecules. So you see that the boiling point and melting point generally increases. As I said, generally increases for boiling point, but melting point doesn't quite follow certain order for melting. Like you realize that built 1 in actually melts at a higher temperature as compared to pans 1 in, and then we're not going to discuss for simple alkene, but we're just going to discuss it for a slightly more complicated alkene. Okay, so that hopefully you can understand why. Yeah, so we are going to deal with cis 1,2-dichloroethene versus trans 1,2-dichloroethene. Okay, now you notice that the boiling point for the cis isomer is higher. Okay, so it has a higher boiling point as compared to the trans isomer. Okay, however, for melting points, it's the reverse. The trans isomer actually has a higher melting point as compared to the cis. And then you might be wondering what is the reason, because for boiling point, right, generally we follow the polarity. Okay, so that means that if there is a net dipole moment, like let's say for cis 1,2-dichloroethene, there is a net dipole moment, we would expect the permanent dipole interaction to be actually stronger as compared to in the case of trans 1,2-dichloroethene, more of dispersion forces. Yeah, so because it has a net dipole moment, stronger PD, so you would expect cis 1,2-dichloroethene require more energy to overcome the stronger PD, so therefore it boils at a higher temperature. Yeah, but for melting is a different thing, because for melting we are really looking at the packing. Okay, what do we really mean by packing? So packing here, so let's see if it's actually in your notes. Okay, so it's not really over here. I'm not sure if it's on. Okay, it's not really over here, but so for packing, right, we are actually looking at how the molecule can pack in a solid state. Yeah, so packing in a solid state here actually means that if you can't really pack very well, so for example the cis isomer, right, because the cis isomer has sort of like a inverted tub shape. So for inverted tub shape, per unit volume, I don't think you can pack a lot of it, but for a trans analog, you can actually pack more. But of course, all these are just, you know, pure discussion, and without actually proof, it's very difficult to be convinced. But maybe all I can say is that if you really look at the solid state structure, you will be convinced that the trans isomer actually pack a little bit better than the cis isomer. Yeah, but I think over here, we do not really have a diagram here to actually showcase to you. So I don't think we will discuss more. But I think for at least over here, the boiling point will be relatively straightforward. Okay, so for alkenes, between the cis and the trans isomer, you notice that the boiling point do not differ by a lot, because as most of you are aware, cis and trans isomer, because alkenes are relatively non-polar, so there will not be any noticeable difference in the dipole moment. Okay, yeah. Okay, so yeah, the melting point actually comes next, so we'll look at packing later. So for exercise 2.1, you're supposed to explain or just choose an option which of the following has the higher boiling point. Okay, so definitely A and B are out, because A and B are just alkenes without a polar group. And then between C and D, of course, there's a net dipole moment going in this direction, so I will pick C. Okay, for the melting point, as we mentioned earlier on, the trans isomer pack a little bit better because of the higher symmetry, and then the cis isomer, because being a tub shape or maybe a U shape kind of molecule, right, it doesn't pack as well. Yeah, so because in a solid state, right, the molecules are relatively immobile due to the fact that very little heat is present, and they are being put in very regular intervals. So in that sense, if they are actually closer to each other, for example, the trans analog or the trans isomer, right, if they are closer to each other, it actually allows stronger dispersion forces to be formed between the electron clouds of the molecules. So stronger dispersion forces actually result in more energy being required to overcome them. Yeah. So in short, when you are looking at boiling point, normally we are looking at whether the molecule has a net dipole moment. Okay, so as to decide whether one has a higher boiling point than the other one. For melting, we are looking at the packing, okay, whether is it efficient or not so efficient. Again, it seems to be a little bit of a pseudoscience, because efficient or not efficient is really difficult to see, because it's all, I mean, we really need to observe the packing in a solid state. So it's actually not very fair to just make a blanket conclusion that, oh, this molecule can pack better than the other one. But what we have shown case to you over here is relatively well understood and relatively simple system. Yeah, you notice that both the like for example, for 1,2 dichloroethene, both the groups on bonded to the sp2 hybridized carbon are the same. So it's actually easier for you to make a judgment call, okay, as compared to, let's say, another molecule where the cis and trans isomer have different groups. Yeah, so in this case, rest assured that, I mean, if assessment question requires, we will give you a little bit more data so that you are able to answer it more convincingly, rather than just blanket rule and say that, oh, you know, like usually the trans isomer packs better. Okay, it may not always be the case. Okay, for solubility, as per, I mean, what we learned earlier on, right? They are relatively non-polar, so usually they will dissolve in polar solvents. Okay, and for density being, I mean, being non-polar compounds and being organic compounds, usually they are not as dense as water. So unless it's chlorinated compound. Okay, so chlorinated alkanes tends to be denser than water. Other than that, most alkenes, etc., they are usually less dense than water, because at the surface or in the liquid state, right, their intermolecular force of attraction is not as strong. So therefore, in terms of density, they are not as well packed or there's less molecules per unit volume as compared to that water. So you expect most liquid alkenes, etc. to be less dense than water. Okay, so and because they do not dissolve with one another, so usually you see a very clear cut 2 layers. Okay, then for viscosity, so for viscosity of alkenes, usually you increase with increasing number of carbon atoms present, because the more when there's an increase in carbon atoms, it actually leads to a stronger dispersion forces between molecules. So stronger dispersion forces here will mean that they are more resistant to free flowing. Okay, so it's like honey. I think I always use this example, like honey versus water. Like because honey is largely carbohydrates with extensive number of OH bonds, so the hydrogen bonding is relatively extensive. So because of that, honey is very viscous, but water is not as viscous. Yeah. So in terms of viscosity, you expect alkenes with a larger number of carbon atoms to be more viscous. Okay, next we're going to move into the preparation for alkenes. For your batch, we decided to take out the contents for the preparation because we don't want to repeat the contents again in the later part of the topics. Yeah, so you're going to learn them for the elimination for HX from halogen alkenes. You're going to learn it in topic 13 under halogen derivative, and for dehydration for alcohols, you're going to learn it under topic 16 on hydroxyl compounds. Yeah, but I can just very in a nutshell to tell you what exactly is going on for the preparation of alkene. So you know that I mean later on in the next topic, I mean in the next section, right, you're going to learn the electrophilic addition of HX onto alkenes. So I will just start off with a very simple example on ethene. Okay, so for ethene, right, there's a CC double bond between the two carbon, and if I'm adding HBr, this is known as electrophilic addition. That's the name of the mechanism. Okay, so perhaps I'll represent the HBr with a different color. Okay, so if I add HBr, I'm going to end up with this particular compound, which is what we call a bromoalkane. Okay, so we're going to end up with a bromoalkane. So there's a H here and there's a Br here. Okay, so this is the forward direction when you subject ethene to gaseous HBr. It is also possible for me to get alkene, in this case ethene, from the corresponding bromoalkane. So bromoalkane is part of the family of organic compounds known as halogenal alkenes. Yeah, so that will be called the reverse reaction. Yeah, take note that this is not an equilibrium, huh? We are using different reagents. Yeah, so that's why I'm writing a full arrow here. So this actually represents one reaction. Okay, I can also do the reversed in order for me to get an alkene. So the reverse reaction, right, is known as dehalohydrogenation, or otherwise called elimination. Okay, so the reagents and conditions is usually we'll usually employ ethanoic KOH and we'll heat under reflux. Okay, so we'll use ethanoic KOH. This might be quite a mouthful, but it doesn't really matter for now. Yeah. So one of the interesting thing about organic chemistry is that any reactions you can do forward, it is also possible to use a different sets of reagents to effect the backward reaction. Yeah, so that is usually how you should study organic chemistry. You should actually link out all the reaction in a huge reaction scheme. Okay, yeah. It is also possible for you to get alcohol directly from alkene. So this reaction is known as hydration. Yeah, so in the process, I will not show you the reagents here because you're going to learn it later on. Okay, so I'm just going to draw out the alcohol. Okay, so yeah, you're going to get a H and the OH here. Yeah, so for the reverse reaction, right, it's known as dehydration because you're removing water here. So for the dehydration condition, usually you employ concentrated sulfuric acid heat. Yeah, so concentrated sulfuric acid usually will, concentrated sulfuric acid is water loving, so it will usually force the reaction mixture to give up its H2O. And you might notice that um, dehydration is similar to elimination, which means it's similar to the elimination of HX over here. Yeah, so to be more specific, these two kind of elimination is what we call beta elimination. Okay, so you're going to learn all this later on. Why is it called beta elimination? It's called beta elimination because, right, it involves the beta carbon. The beta carbon is the carbon next to the carbon bonded to the Br. So this is alpha, this is beta. Okay, so this is alpha, this is beta. So in order for elimination of water or elimination of HX to take place, you need to ensure that the beta carbon contains a beta hydrogen. Yeah. So in short, usually we call these reactions beta elimination. Okay. Now, anyway, please look forward to learning them next year. It's going to be a lot more interesting as compared to what you're learning now. Okay. We're going to move on to the next part on alkenes, which is our focus in this chapter. Okay, which involve the reactions of alkenes. Yeah, so in a very simple fashion, I'm just going to introduce to you what we call electrophilic addition. It's called electrophilic addition because the inorganic reagents, in this case, usually it's inorganic, which approaches the alkene, right, is usually what we call electrophile. Yeah, so in this case, an addition reaction occurs because the unsaturation is being removed. Okay, so that it's not going to lead to any side products being released. Okay, yeah. So the general mechanism follows this particular fashion. So there are usually two steps. I use the word usually because for simple electrophilic addition is two steps. Usually involve one slow and one fast step. Yeah, the slow step is usually the first step, which generates the carbocation. The reason why the first step tends to be the slow step, because the stability of the alkene is being disrupted. Yeah, it leads to the formation of a carbocation which contains only 6 electrons around it. So it's a highly unstable intermediate. Yeah, the next step, which is step 2, is usually the fast step because the unstable carbocation, right, will be attracted towards the nucleophile, which is negatively charged, and it is attracted due to attraction between opposite charges. Yeah, and such reaction is usually barrierless. Yeah, so the next step is usually the fast step. Okay, so that's the generic mechanism for electrophilic addition, but do take note that your electrophile need not be positively charged in the beginning. Yeah, I don't want you all to have the impression that electrophile must be positively charged at the beginning. It need not be. Okay, it could be a molecule with an electron deficient site. So for example, HBr, it is electron deficient at the hydrogen. Okay, due to the polarity difference between H and Br. Yeah, so we will call H the electron deficient carbon. Sorry, the electron deficient hydrogen, or you can call it the electrophilic hydrogen. Yeah, but in general, we call HBr the electrophile. Okay, the carbocation intermediate is formed in the first step or in the slow step of electrophilic addition. Yeah, so in general, carbocation looks like this. So it has a positive charge center at the carbon, bonded to 3 different groups, and there's only 6 electrons around the central electron deficient carbon. Yeah, so that makes it highly reactive, and it's usually trigonal planar in geometry in most cases. Okay, I said usually, but I think for H2 wise, it's almost always all the time. Okay, trigonal planar geometry give it some interesting perspective because if the nucleophile is present nearby, it will be able to approach it from either side of the plane. So if you look at the trigonal plane in this fashion, it's planar, right? So we have the top face or the top plane and the bottom plane. Yeah, so the electron reach nucleophile can approach the top and the bottom plane with near equal probability. Yeah, so if all your three groups are different, you're going to end up with a racemic mixture. Okay, so that is also an important characteristic of electrophilic addition. Okay, stability of carbocation is relatively similar to that of radical. Yeah, so in general, I think we mentioned earlier on that LQ groups tends to be electron donating. Yeah, so the more LQ groups the carbocation is being bonded to, the more stable it will be. Okay, so in this case, I think the stability of carbocation needs no introduction, from left to right, less stable to the most stable, because for a tertiary carbocation, it is bonded to 3 LQ groups as compared to the rest with 2 or less LQ groups. So in this case, the carbocationic center will be slightly more stabilized as compared to the rest. Yeah. Remember that stability is a relative term. So it doesn't mean that the tertiary carbocation being more stable means that it will exist for a very, very long time. Yeah, it doesn't mean that way. So it just means that it will tend to be formed because the activation barrier leading to its formation is lower. Yeah, so yeah, I mean, I think what we are teaching over here is in a slightly more generic way. There will be a lot of details which you, if you really want to understand, you really need to read beyond what you are given in the notes. Yeah, so I really encourage all of you to go and read on some of the text, on the text I uploaded on our Google Classroom, or you can just look for information online. I think that will help a lot. Okay. What else should I mention? Okay, so electron donating group stabilizes carbocation. So the more electron donating groups you have, the more stable will the carbocation be, and then the activation barrier leading to its formation will be lower. Yep. And there is a shortcut way of representing carbocation in the sense of primary, secondary, or tertiary. So primary, we can write it as 1 degree, secondary 2 degrees, tertiary 3 degrees. However, please take note that this should never be pronounced as it is, meaning you shouldn't pronounce primary carbocation as 1 degree. Okay, you'll just make you look silly. Okay, so it should be pronounced as primary, secondary, and tertiary. Okay, yeah. Maybe it is also worth mentioning that not only will electron donating group stabilizes carbocation, if I have a pi system next to it. So for example, let's say I look at this particular carbocation. Okay, so this particular carbocation, based on our definition here, is actually primary. Why is it primary? Because this, the H right at the end, I mean the carbon right at the end, is bonded to 2 H's. Okay, however, this primary carbocation is exceptionally stable. Yeah, in terms of stability, it could be as stable as a tertiary carbocation, if not even more stable than a tertiary carbocation. Why is that the case? Okay, because if you look at this particular primary carbocation, right, it is conjugated to a CC double bond. So if you look at the CC double bond next to it, it contains a pi system, okay, and then this particular carbon over here, right, has an empty p orbital, okay, empty p orbital with a positive charge. So because they are all parallel, you expect delocalization, okay, to take place, or rather not take place. You realize that delocalization could occur for such a carbocation that is conjugated with a CC double bond or with a pi system. So a pi system can be CC double bond, or it could be a benzene ring. Yeah, it really depends. Yeah, so do take note that the stability of carbocation is not simply restricted to primary, secondary, tertiary, or number of R groups bonded to it, but you should also take notice of the potential stabilization which could have taken place when it's next to a pi system. Okay, yeah. So for the electrophilic addition of HX, we are looking at a generic HCl, HBr, or HI. Usually we don't look at HF. Again, similar to the earlier topic on alkenes, HF has some exceptional kind of reactions or stabilities we are going to talk about I mean, we're not going to talk about H2, but if you are really interested in, you can read more about it. But in order to add fluorine, you can't use HF. Yeah, it doesn't work in a normal way because number one, the HF bond is relatively strong. Okay, it's like 562 kilojoules per mole as compared to the rest of the hydrogen halides. Okay, so normally when we put HS, we are really talking about HCl and HBr. In fact, even for HI, the CI bond being relatively weak, its occurrence again, I mean, when the corresponding alkyl compound form, it might not be stable enough for you to isolate. It really depends. Okay, so generally HCl and HBr are the one that we are dealing with. But of course, for the purpose of covering the curriculum, HI will be okay as well. Okay, so the general mechanism begins with the pi system attacking the electron deficient hydrogen, which leads to the heterolytic cleavage of the HBr bond. Okay, so you realize that when the arrows are being drawn, right, it's a full arrow. Remember, I mentioned that for alkene, it is probably the only time you're drawing a half arrow or a fishhook arrow. Okay, for other reactions, we call these reactions polar reactions. So usually involve the pi bonds being electron rich, attacking an electron deficient hydrogen, and we must draw it with a full arrow head. So this is a full arrow head, and then it leads to the heterolytic breakage of the HBr, and then we need to draw it towards the electronegative Br. Okay, so remember that when you draw your arrow, you draw it towards the H. Okay, and when the bond is broken, it's drawn towards the Br because the lone pairs of electrons is being formed. Okay, of course, here we need to take note that HBr alone, the Br already have three lone pairs of electrons. So this particular HX or HBr bond, the sigma bond, when it's broken, the new lone pair of electrons will be being given over here. Okay, and then it leads to the formation of a carbocation. The first step is the rate determining step, as we mentioned, because it involves the formation of unstable carbocation. Yeah, because on their own, they will rather exist individually. Okay, yep. And then I'm going to move on to the next part. Then the next step is a fast step, which involves the bromide nucleophile attacking the electron deficient carbocation. And remember that when you draw your arrow, you must point at the carbon and not point at the charged. So if you draw it this way, you'll be marked wrong. Okay, so this is incorrect. Okay, you must point at the carbon because you are forming a bond between Br and the carbon. Okay, so remember this. Okay, and maybe for assessment purposes, I should also mention that whenever you are asked to draw the mechanism or illustrate the mechanism or propose the mechanism, yeah, if you see all these command words, right, you are simply required to just draw step 1 and step 2. There isn't a need for you to describe everything out. Okay, so remember this, there isn't a need for you to describe everything out. Okay, so that's why if you are very strong in understanding reaction mechanism, usually you can answer an exam question relatively fast because drawing mechanism is really in your DNA. Okay, yeah, so remember this, don't need to explain all the words. Unless, of course, there are some novel mechanism where if it's ever being asked in H2, they'll ask you to draw the mechanism and then maybe briefly explain maybe one of your steps. Yeah, I mean, it happened before, so remember, read the question carefully. Yeah, other than that, usually when they ask you to illustrate, draw, propose, suggest, mechanism, usually drawing itself is sufficient. Okay, and it is also important for you to take note that there is a need for you to indicate the slow and the fast step, okay, in your drawing. Okay, so remember to indicate the slow and the fast step. Yeah, okay. For the energy profile diagram, remember earlier on I mentioned that why is it that the first step is slow, right? Because it leads to the generation of unstable carbocation. Okay, and that is why the relative energy between the carbocation and your starting material, okay, the carbocation is of a much higher energy. Okay, and then in the course of reaction, it goes through what we call a transition state. So this portion is what we call a transition state. Okay, it is also worth mentioning here that in case you didn't remember what you learned in secondary school, a transition state, right, is different from an intermediate. Okay, I need you all to remember this. Transition states are transient species which occurs say less than 10 to the power minus 15 seconds, and this actually leads on to a new area of chemistry known as femtochemistry, because femtoseconds is 10 to the power minus 15 seconds. Okay, intermediate usually can exist in a time frame between 10 to the power minus 6 to 10 to the power minus 8 seconds. So intermediates can be studied and can be detected in the course of a reaction, but transition state cannot. So usually, okay, so the major difference between transition state and intermediate, I mean, in addition to their period of existence, right, is also the fact that intermediate already have all the necessary bonds being broken and being formed occurring. So that means that an intermediate itself is really a species which you can so-called isolate and maybe study if it's stable enough. But transition states usually contains, okay, let me mention, usually contains partial bond breaking and forming. Okay, so how do you represent partial bond breaking and forming? Maybe I can just illustrate one over here. So maybe just let me erase this part first. Okay, so let's say we call okay, so I'll illustrate it here. So these are just some additional information you might want to take note of. I mean, for academic, or rather for full understanding. Okay, so I call this TS1. So this is the first transition state, and then I call this TS2. Okay, the first transition state, right? Okay, as I said, partial bond broken and partial bond forming, right? Yeah, so and it leads to the formation of a carbocation, right? So you would expect the first transition states. Okay, so maybe I should draw on the left. The first transition state will look something like this. Okay, with and then a dot line. Okay, so that shows you that the pi bond is being partially broken. Okay, and then I need to draw another dot line to show that the sigma bond between H and carbon is being partially formed, and then another dot line between H and Br to show that the sigma bond between H and Br is partially being broken. Okay, so usually transition state is represented with a square bracket with a double dagger. So this unique sign, right, is called a double dagger. Okay, so that might be something that you want to take note of. Okay, and then so this is TS1. And then for TS2, it will look like this. Okay, so again, a big square bracket. So for H, carbon, H, and an H here, and then a C, and then a H, and a H, right? So again, we have a dot line. So dots, and then Br. So it's a Br negative charge approaching the transition states. So you can draw a minus and a plus here if you wish to, but actually doesn't really matter. Yeah, so it shows the formation of the Br carbon bond. Okay, some of you might be wondering, does it matter regarding the length of these partial bonds? Answer is yes, absolutely. But obviously, in this case, I'm not going to show you the difference because it's not important for the case of H2. In fact, the drawing of transition state for H2, right, is only important for one of the chapter, which is chapter 13 on halogen derivative. Okay, and we will deal with that later on. Okay, so we have the next exercise 4.1. Okay, so it was being asked, hydrogen bromide reacts with ethene to form bromoethane. What is the best description of the organic intermediate in this particular reaction? Okay, so let's look at the top. Your organic intermediate is the one I'm going to highlight in yellow. So this is the organic intermediate. Remember I mentioned earlier on, the organic intermediate is actually electron deficient at a carbocationic center. And any electron deficient sites, what do we call them? We call them an electrophile, right? Okay, right? This is the electrophile. It cannot be a free radical because there's no unpaired electrons. It doesn't contain carbon, hydrogen, and bromine because the bromide have yet to attack the electron deficient carbon, and there's no negative charge because the carbocationic center is positively charged. Okay, so the only answer here you can give will be C. And then there's also one thing that I thought is worth mentioning, but I hope that by mentioning that it doesn't confuse you guys. That is of what we call a role reversal. Okay, now you notice that okay, so in the electrophilic addition of HBr on alkene, right? So I'm just going to go up here, right? You notice that the electron-rich site is actually the pi bond. So we will call the alkene a nucleophile. Okay, and then of course we'll call HBr the electrophile. Okay, now you notice that when the carbocation is being formed, right? Originally the alkene is the nucleophile, right? Now it becomes the electrophile. And then the HBr, now the bromide becomes the nucleophile. Okay, so that is what I meant by role reversal. Yeah, so it is true that you are not going to be an electrophile for the rest of your life, or you're not going to be a nucleophile for the rest of your life. It really depends at that stage, in the stage of the reaction, what exactly is happening. Okay, yeah. So we're going to move on to the addition to an unsymmetrical or asymmetrical alkenes. Okay, now earlier on you notice that in our examples, right, the alkenes are perfectly symmetrical, so meaning that regardless of whether the H is being added to the first carbon or the second carbon, it doesn't really matter. But what if it's an asymmetrical alkene? What is going to happen? Yeah, so it will lead on to what we call a major and a minor product. And then traditionally, this will be called what we call the Markovnikov's rule. But now, because we already know what exactly is happening, we can explain to you why. Okay, now you'll notice that I'm going to highlight this particular hydrogen here with yellow. Okay, so now when the hydrogen is being added to the first carbon, okay, it forms a primary carbocation. If the hydrogen is being added to the second carbon, you actually produces a secondary carbocation. And as we learned earlier on, right, the secondary carbocation is actually more stable. So the activation barrier, right, leading to the secondary carbocation should be lower. Okay, so in that case, it will be formed in preference to the primary carbocation, and because it's formed in preference, more of it will be formed, and then the bromide will then undergo a nucleophilic attack on the secondary carbocation to give you the final product. So 2-bromopropane will end up as the major product. Okay, so one bromopropane will end up as the minor product. Yeah, so that is probably something which you might be interested in. Okay, as you study. Okay. Yep. And then I'm not very keen in talking about Markovnikov's rule because Markovnikov's rule, as I always share with students, is like a no concept rule. Yeah, but if you want to, you can read. Basically, they're just saying that if you're adding to an asymmetrical alkene, the H is usually added to the carbon with a greater number of H. Yeah, and if you realized, in this case, if it's being added to a carbon with a greater number of H, you end up with a more stable carbocation, and that is the reason why, yeah, it's being added in that particular way. So in short, you don't really need to know Markovnikov's rule in order to predict the product. Yeah, you can simply predict the product based on the stability of the carbocation form. So I don't want you to be stressed in trying to memorize so many rules because in fact there isn't a need to. You simply just need to be able to predict which is the more stable carbocation being formed, and that's about it. And you are almost done for alkenes. Okay. I think there's a whole bit over here to explain to you why. Yeah, so I think I will not spend too much time here, but basically the more stable carbocation will be formed because there's more electron donating group to stabilize it. Yeah, so because of that, the activation barrier leading to its formation is low. I think I mentioned all this earlier on. Okay, then with this, again, we have another asymmetrical alkene here. So this is actually more stable because it's a tertiary carbocation. This is less stable. So it's a secondary carbocation. We will not say that it will not be formed. Okay, we are just saying that the amount of it being formed is much lesser as compared to the more substituted or compared to the tertiary carbocation for that matter. So therefore, this will be the major product. Okay, yep. So for exercise 4.2, we are just going to predict the major product. In fact, I think the answer will be quite similar. Yeah, okay, to the above. Okay, so if you are drawing the mechanism, you know that if my HBr is like this, okay, and then I'm going to have a polarity difference, so the pi bond attacks H, and then breaks towards the Br. Likely that I'm going to end up with a carbocation here, which is a tertiary carbocation. And then, so the first step is actually the slow step. So this is the slow step. Okay, and then for the fast steps, I expect the bromides, okay, undergoing a nucleophilic attack on the electron deficient carbocationic carbon. And then in the process, I will generate this tertiary bromide alkene. Okay, yeah, so I think that's about it. I think it's pretty similar to the one, actually, in fact, it's the same as the one above. Okay, yeah, if you're asked to draw the minor products, then you should be drawing this. So in general, if you're not asked to draw the minor products, you can simply just illustrate the mechanism leading to the major products. Okay. Now, I think earlier on I have kind of give you a preamble in that carbocation is actually trigonal planar in geometry. Yeah, so if we have an alkene here, we are going to generate what we call a trigonal planar carbocation with three unit groups: CH3, CH2, CH3, and H. Yeah, so these three unit groups, right, allow the bromides, okay, I mean, it's not allowed, but these three unit groups will result in the fact that I will end up with an enantiomeric pair because the bromide can approach the carbocationic carbon from the top and bottom plane with near equal probability. Yeah, and how do I know that they are an enantiomeric pair? Basically, I can draw a mirror plane here, and then you can sort of tell that this is like a mirror to this, a mirror to this, it's a mirror to this, and this, and this. Yeah, so they are enantiomeric pair. You'll be I think one immediate question you'll be asking is, what if these two groups are the same? Yeah. So if these two groups are the same, I will not end up with a compound with a chiral carbon. So in that case, it doesn't matter whether it approached from the top or bottom plane because I will still end up with the same compound. Yeah. So no doubt that if the two groups are the same and the bromide will still approach it from the top and bottom plane with near equal probability, but I will not end up getting a racemate mixture because to begin with, there is no chiral carbon. Okay, so I think you have to be really careful whether your final product contains a chiral carbon or not. Okay, now what about electrophilic addition of halogens? Okay, so electrophilic addition of halogen pretty much follows similar mechanism to that of HBr or HCl. Okay, but in our case here, I think we need to make mention that usually we are simply dealing with chlorine or bromine, or in that case, chlorine and bromine dissolved in CCl4. Yeah, we do not normally allow alkenes to react with fluorine because it's simply too reactive, or even with iodine because it's not reactive at all. Okay, so in order for alkenes to react with iodine, we need to use other forms of compound in order to generate the electrophile. Okay, yeah. Then, yeah, so the mechanism follow the same fashion. So then you'll be wondering, I think one immediate question you might have is, why is there a delta plus and a delta minus here? Okay, so the delta plus and delta minus is due to the polarization of the bromine electron cloud when it approaches the pi electron cloud of alkene. Yeah, so when the pi electron cloud approaches the bromine, it will polarize it in such a way as to temporarily generate a delta plus over here and a delta minus. And this delta plus being generated, right, will result in electrophilic addition to occur. Okay, so again, it will generate this carbocation, And then similarly, the fast step involved the bromide approaching from the carbocationic carbon in the fast step. Okay, some of you might read it, you might read a little bit more. Okay, I mean it's worth mentioning that a lot of research has been done on electrophilic addition because all these are very old chemistry. They are usually being done in the 40s, in the 1940s, 50s, and 60s, right? They actually realized that in the electrophilic addition of bromine, it undergoes through. I mean, it undergoes the reaction undergoes via an intermediate which is uniquely looking. It's known as a cyclic bromonium. Yeah, so this is something that we are probably not going to go through in H2, but I think is worth mentioning. Yeah, so this particular cyclic bromonium intermediate is able to lock the stable chemistry such that when the bromide approaches it, it will approach it from the opposite side. Yeah, so that is why people actually notice that electrophilic addition of halogen, right, is what we call a trans addition rather than a cis addition. Yeah, so meaning that when this is being locked, right, the bromide can only approach it from the bottom. Yeah, because so if I'm going to sketch the 3D, right, so when it's being locked, it is sort of being locked in this particular fashion. Okay, yeah, so when it's being locked in this particular fashion, the only way for me to break this bond, right, is that my bromide nucleophile must approach it from the bottom so that this can break. Some of you might be wondering, how come approach from the top cannot? Okay, then I think I will attempt to explain this maybe in a tutorial rather than in a lecture setting. Yeah, so it can only approach from the bottom. Because as you're going to learn in in the chapter 13 on halogen derivative, right? This is some form of a nucleophilic substitution reaction, similar to a nucleophilic substitution. So nucleophilic substitution usually occurs from the rear of the C halogen bond. Yeah. So in this case, this is the C halogen bond, and this is the carbon, and this is the rear of the carbon. So it must approach from the back, not the front. Yeah. As to the reason why, I think we'll deal with that when the time comes. Okay. Yeah. So because of that, electrophilic addition of alkenes, right, with halogens, usually result in what we call a trans addition rather than a cis addition. Okay. Yeah, but this is not in the curriculum, so we will not attempt to discuss too much on it. Yeah, but do take note that sometimes for assessment, some clues can be given to you in the context of the question based on the preamble or the context of the question. So you need to explain your answers based on the context. Okay, so yeah, I will not probably go into more details. I mean, when the time comes, then you will deal with it, or when you become a little bit more familiar with chemistry, then I think some of these things will be something that which you can accept more readily. Okay, the next thing I'm going to discuss is electrophilic addition of bromine water. Yeah, so in this case, what exactly is bromine water? So basically, it's bromine dissolving in water. Yeah, so as you might have seen in the lab, it's a bit orange yellow in color. Yeah, so this is usually used as a distinguishing test for alkenes. Okay, because when you add bromine water, it will usually decolorize, and the decolorization is some sort of a test for unsaturation as well. Okay, the mechanism follows what you learn under halogen. So the first step, or rather the slow step, usually involve the electrophilic addition of bromine, in this case the halogen, and it will lead to the formation of a carbocation. However, when a carbocation is being formed, right, some of you might be wondering, how come there's an OH? Where does the OH come from? Right? Okay, the OH actually comes from water, which is a competing nucleophile, because water also has lone pairs of electrons on the oxygen. Yeah, so in the first step, there will be two competing nucleophiles, water and bromide. But water being the solvent here, right, it exists in much greater amount as compared to bromide. Yeah, So in this case, if you want to compare water and bromide, water will win because there are a lot more of it. So yeah, so water will undergo a nucleophilic attack onto the carbocation, and in this case, you will form the bromohydrine. Okay, you might be interested to know the name of this compound because it's actually quite important for you to know the name. Okay, this is known as a bromohydrine. Okay, it's like a hydrated bromoalkene, something like that. Okay, yeah. Okay, so they showcase to you the mechanism over here. Yeah, you might be interested to know that the first step is not a simple step because when the water molecule actually perform a nucleophilic attack on it, right? It is the whole water that attacks and not OH minus. Okay, so when water molecule attacks it in the first step, right? You notice that the oxygen will take on the positive charge from the carbocation. As to why the oxygen takes on a positive charge, again, we'll discuss it maybe in the tutorial setting, or you can explore it a little bit on your own. But as I said, it might not be very important for you guys to pay so much attention to it. Yeah, and then later on, the H will be deprotonated by either water or bromide here, and then it will lead to the bromohydrine, in this case bromoethanol being formed. Okay, of course the bromide can attack, but as I said, the concentration of water is much greater, so the probability of water attacking is much higher. So remember that in chemical reaction is always a probability game. So because it's a probability game, right, when it exists in much greater amount, the chance of it attacking the electron deficient carbocation is much greater. We have an exercise 4.3 here. So you're asked to predict the product form when proteins react with bromine water that is contaminated. So let me highlight this interesting line. Contaminated by aqueous sodium chloride. And then you're supposed to explain why it is not possible to obtain 1,2-dichloropropane. Okay, so first of all, right, I think I hope we are on the same page. We should be able to appreciate that the first step must involve the electrophilic addition of bromine. Okay, and it can only involve bromine because bromine is the electrophile. So this is the slow step, which is the first step. Okay, so remember that when you draw your mechanism, the pi bond attacks the electron deficient Br because it's being polarized, and then the Br bond breaks heterolytically. Okay, and then of course I will draw the more stable carbocation being formed. So this is the one I'm going to draw. The Br is over here, and then this is the carbocation being formed. Okay, and then of course I will have a bromide here. Okay, so this is the first step. Okay, however, right, this particular carbocation, okay, there are three potential nucleophiles present in the system. You notice I highlighted that phrase, contaminated with sodium chloride. Okay, so first of all, right, is the same as what we have above. The water will compete with it. Okay, so water will then compete with bromides, and then water molecules will attack this, and then in the process I will form the hydrated, or rather the protonated alcohol. Okay, and then of course this is the first step, and then the protonated alcohol will lose a H plus, and then in the process I will be able to get this particular OH, this bromohydrine. Sorry, I mean I can't really write very straight over here. Yeah. Okay, sorry. This line is a bit difficult to draw. Okay, and then the next potential products I will be able to get involve the bromide nucleophile. Okay, is what we have over here. Okay, so attacking this particular carbon. Okay, so I'm going to get 1,2-dibromopropane. Okay, the next product I'm going to get of course involve chlorides, because sodium chloride contains excess chlorides, right? So chloride will then attack this carbon, and then in the process I'm going to get bromochloroalkane. propane. Okay, so this is the propane I'm going to get. Okay, it's to be more specific, it's 1 bromo 2 chloropropane. Okay, and then the final part of the question being asked is, why is it not possible to obtain 1,2-dichloropropane? Okay, so again, remember what we said earlier on, the only electrophile present is bromine. Okay, there isn't chlorine electrophile. Yeah, so or there isn't any source where I can generate either Cl plus or even chlorine molecule. So without these two sources, I will not be able to insert the first chlorine in. Yeah, so that's why you will never get 1,2-dichloropropane. Okay, yep. And then if you recall what we said earlier on under the section 3, right? This is electrophilic addition of water or steam to generate the alcohol. Yeah, so please remember the condition, because generally students do not really remember this condition very well. There are two methods of generating alcohols from alkenes. The first method is what we call the industrial method, which uses steam and phosphoric acid as the catalyst. Okay, however, right, you need to operate it under high temperature and high pressure. Okay, the next method is what we call the lab method. Yeah, you are required to know both methods really well, because sometimes you are asked to use the lab method instead. Yeah, so for the laboratory method, you are supposed to incorporate cold concentrated sulfuric acid inside. Okay, and then after that, this is followed by adding water in the next step. Okay, so the 1 and 2 here, right, take note, they are not added together. So it's one after another. So the first step, you need to incorporate concentrated sulfuric acid first, and then after that you use water to either hydrolyze the intermediate being formed or to replace whatever intermediate group that actually attached to the carbon in question to generate the alcohol. Okay, so you are asked to refer to the appendix for the mechanism, which we're probably going to deal with that a little bit later on. Okay, so what alkenes would you start to prepare the following? Okay, so I think we can do that relatively quickly. So again, I'm going to count the carbon. So I'm going to have 1, 2, 3, 4, 5. Okay, so which alkene do you think I will begin with? Well, I mean, it should be quite obvious, because to begin with, carbon 2 must be the carbocation. I hope you agree with me on that. So if carbon 2 is the carbocation, so potentially I can have something like this. 1, 2, 3, 4, 5. Yeah, I can have this particular terminal alkene where I add a HBr to it, and then carbon 5 will gain the hydrogen, and then carbon 2 will be the carbocation. Okay, or I can have a double bond between carbon 2 and 3 as well. Okay, so I can have this particular CC double bond between carbon 2 and 3, and then so 1, 2, 3, 4, 5, and then when I subject this particular alkene to HBr, the hydrogen will be added to the third carbon, and in this way I will generate a tertiary carbocation, and then the bromide will attack the tertiary carbon 2. Okay, or rather tertiary carbocationic carbon 2. Yeah. For part B, should be relatively straightforward as well. So again, I am going to do the same thing. So 1, 2, 3, 4, 5, 6. Okay, so I'm going to draw out the compound. Yeah. So let us try. So in order for me to get this particular alkene, I think, to get this particular alcohol, maybe I can start off with something like this. Okay. Of course, take note that there are competing products. Yeah, so if I'm going to subject this particular compound to steam, right, potentially I can get other products as well, because the OH can also go into the other two carbon. Okay, that is possible, or I can have a mixture. Okay, so yeah, so this is one potential starting material I can have, but bear in mind that in the process, I will not generate this exclusively. I will generate other potential competing products. Okay, some of you might be wondering whether it is possible for me to start with, let's say, something like this lah. Okay, this is not ideal because if I start off with this, right, you realize that in the electrophilic addition, right, I will actually generate a carbocation here. Okay, so let's say I already undergo electrophilic addition here. So yeah, so this carbocation, right, it will actually result in this particular alcohol being predominantly formed. Yeah, because this is actually formed from a tertiary carbocation. Yeah, yeah, but for the earlier example, right, I am only generating secondary carbocation, and because of that, there is no preference. Yeah, of course, there will be some preference depending on steric hindrance, but in general, I think the preference is very little. So, and it's not selective. So in that sense, I would rather um, leave things to chance. Yeah, so that's why we propose something like this. Yeah, but if we propose the other alkene, which is the conjugated version, then we're going to run the risk of getting a lot of potential side products. So therefore, it's not entirely desirable. Okay, yeah. The next part is reduction, or what we call catalytic reduction, which uses nickel catalyst, room temperature, high pressure. Yeah, so you would have learned this in secondary school, or you would have seen this in under reaction kinetics. Yeah, so for this particular reaction, actually there are a lot of metals which you can use. You can use palladium, you can use platinum, you can use nickel, you can even use rhodium, ruthenium, but take note that different metal may require slightly different conditions. Yeah. Okay, so in general, I think in our notes, we just give you nickel, which takes place at room temperature condition. I think this is easier to manage. Okay, yep. Um, there's a part for you to take note of. H2 with nickel catalyst is also able to reduce other functional groups. Yeah, so we'll discuss them in later topics. So just take note that this is not exclusive to alkenes, CC double. Yep. Okay. The next portion is probably another important portion, and is probably another subsection which students will find it challenging. It's called oxidation. Okay, the mild oxidation is not challenging at all because I think it might be quite obvious for most of our students. So for the mild oxidation, right, basically the condition is potassium permanganate with alkaline condition, in this case sodium hydroxide, and take note that it must be cold. Okay, and in this case I will form a diol over here. Okay, so take note that this is not electrophilic addition. Okay, I think it's worth mentioning this. This is not electrophilic addition. So oxidation condition, I mean, no doubt the mechanism eventually, if you read beyond H2 curriculum, right, may involve some form of electrophilic addition. But in general, we don't want you guys to learn it as electrophilic addition. Yeah, so in general, we will call them either mild oxidation or strong oxidation, or what we call oxidative cleavage. Okay, and also take note that similar to the earlier portion or earlier chapters, right, we will balance the equation using bracket O. Okay, we will not do the redox balancing unless the question requires you to do so. Yeah, so please remember this. Okay, so in general, when you're asked to write the so-called balance equation, you do not need to incorporate permanganate as the species. Okay, yeah. The observation is also worth taking note of. Purple permanganate will decolorize and you will get brown PPT of MnO2. Yeah. This is as opposed to strong oxidation condition where the purple permanganate decolorize to give a colorless solution, which is Mn2+. Yeah, so there is a slight difference. So you might want to take note of the difference in conditions as well. Okay, the next part is oxidative cleavage. Again, worth mentioning because oxidative cleavage is probably the most important portion we're going to mention under alkenes. Okay, so for oxidative cleavage, it's a little bit mechanical, I would say, in determining the product. Yeah, so I will go through it in a little bit of details, but I think before that, maybe just let me highlight to you what exactly is going on or what exactly might happen. Okay, so for oxidative cleavage, right, what is most important for you to take note of is the condition. So you have KMnO4 as well. But instead of alkaline condition, you use acidic condition. Okay, and instead of cold, you need to heat it. Okay, and this actually decolorized. It may lead to the effervescence of CO2 depending on whether CO2 is a byproduct. Okay, depending on that. If not, then I think the observation you want to make will be the decolorization of purple KMnO4. Okay, and in oxidative cleavage, how do we predict the product? So that's what we're going to go into next. Okay, but okay, so before we go into that, I might want to remind all of you that the oxidation of alkene cannot be carried out using potassium dichromate. Okay, so this is important, cannot. Because a lot of your seniors, they get confused. So they thought that potassium dichromate can do that as well. So cannot. Only KMnO4. Okay. Some of you might also be interested in the mechanism of oxidative cleavage, but take note that the mechanism is not within H2 curriculum. And usually strong oxidation condition for alkenes is not a very well studied reaction because it occurs too rapidly and in most cases difficult to study during that period of time. Okay, that's in the 40s and 50s. And in general, because oxidative cleavage generates too many side products and is not easily controlled, so synthetically it is not a very useful reaction. Yeah, so I need to emphasize that oxidative cleavage probably is only important at the theoretical level. Yeah, because synthetically, meaning in order to make molecules, we will need to employ certain reagents in order to do transformation from molecule A to molecule B to C, right? Oxidative cleavage is too, I mean, using KMnO4 is too strong. KMnO4 is too strong a reagent that it is not synthetically useful. Yeah, so in that sense, we are really not too concerned over its mechanism, and that's also probably the reason why it's not well studied, even at the most advanced level. Okay. Yeah, so now I'm going to go through with you some of the important things regarding oxidative cleavage, and hopefully you will find them useful because the prediction of oxidative cleavage products will remain as maybe one of the most challenging part in your studies of this particular topic. Yeah, so perhaps let me make mention to how to predict the products, and then it will help you in this particular journey. Okay, so the first thing I thought, okay, so you might want to be familiar with this particular table, but if you I mean it's kind of a good summary, but I just thought that I could explain a little bit more later on. Okay, so now when oxidative cleavage occurs, right, generally the CC double bond is being cleaved. Okay, so it will be cleaved. Okay, so remember the mechanism is not important, so we just need to know that the CC double bond is being cleaved. Yeah, which is probably more important than anything else. Okay, now again, we are not so concerned over what exactly is the blue box over here. Okay, we're not so concerned because over here, right, we are mainly concerned with what will result in the right hand side. Yeah, because if you are able to predict what happened on the right hand side, right, on the left hand side is basically just another combination of whatever we have on the right. Yeah, so you will be able to predict the product. Okay, so the first thing you want to do, right, is, okay, so let me just guide you through. You draw the same thing, sorry, you draw the same molecule, okay, with the groups. Okay, so I will just draw the same thing with the groups. Okay, sorry, I used the wrong word. It shouldn't be molecule, the species. Okay, so this is the one I've highlighted in pink over here. Okay, I'm going to draw them. Okay, and then I'm going to replace the double bond with a double bond oxygen. Okay, so I'm just going to replace it with a double bond O. Okay, double bond O, double bond O. And then I'm going to ask the first question. You have to ask yourself the first question. What kind of compound is this? Okay, so this is basically a ketone. Okay, so yeah, so in this case, you need, at this moment, right, you need to flip back into your introductory organic chem to understand the difference between a ketone and an aldehyde. Yeah, so a ketone is where you have a carbonyl group and then bonded to two R groups. So we call this a ketone. So after you replace it with a double bond O, if it's still a ketone, right, then you just draw this as the final product. Yeah, so this will be the final product that you will draw, which is a ketone. Okay, then if it's not a ketone, it will be an aldehyde, which is what we have over here. Yeah, so this is an aldehyde. Now, an aldehyde, remember that in strong oxidation conditions, such as the presence of KMnO4, it will be further oxidized to a carboxylic acid. Okay, why is that the case? Okay, I can kind of explain to you that because your CH bond is the weakest link over here due to the presence of the carbonyl oxygen. Yeah, so that means that your CH bond in this case is sort of activated towards oxidation condition. Yeah, so since it is being activated, right, so I will not be drawing this cage because it wouldn't be formed. So it will be further oxidized to a carboxylic acid. Okay, which is what I'm going to draw over here. Yeah, so you'll be drawing a carboxylic acid. So the final product you're going to draw is a carboxylic acid. Okay, yeah. And then after that, you'll be wondering, how come terminal alkenes, which is the one with CH2, gives me a different product? Well, you need to look at this particular compound. This is actually a special aldehyde known as formaldehyde. Okay, formaldehyde, which contains two activated CH bonds. Okay, so that means that these two CH, right, will be further oxidized to give me carboxylic acids. And this particular carboxylic acid is what we call, is actually present in your soft drinks. It's what we call carbonic acid. If you remember it, we talked about it in the earlier chapter, I think in redox. I think it should be redox, yeah. So carbonic acid is actually not stable in aqueous medium. So it will quickly decompose to give you CO2 and water. Yeah, so take note that carbonic acid is not stable in aqueous medium, so it will very, very rapidly decompose to give you CO2 and water. And that is why you get CO2 as the side product, or sorry, byproduct. Okay, yeah, so in short, to summarize what you should be doing, okay, so first of all, you cleave, and then you draw the part in blue, okay, which I did earlier on, and then you replace the CC double bond with a double bond O. And then you ask yourself, is this a ketone? If it's a ketone, you keep it, okay? If not, you'll be an aldehyde. So an aldehyde will be further oxidized to a carboxylic acid. Okay, yep. But please take note that oxidative cleavage does not always mean that I'm going to get two separate compounds. Okay, so what I meant is, if I have a long alkene like this, and then another long alkene, okay, if I undergo oxidative cleavage, I'm going to get two products. Okay, no problem. Okay, however, right, if it's a cyclic alkene, and I undergo oxidative cleavage, okay, my product will still be one whole product, which will be like this. Okay, yeah. So it doesn't mean that oxidative cleavage only give me one product. I can end up with two products. Sorry, only give me two products. It's possible for me to end up with one product if, let's say, the oxidative cleavage occurs in a CC double bond within a ring. Okay. There is also the special case of oxidative cleavage where you only end up with CO2. We probably don't want to call it a special case, but I mean, if you wish to call it, you can. So normally, I don't want to make mention of this portion separately because it's actually not so crucial. But I think maybe I should. Okay. Now, you notice that this particular portion, right, is pretty much the same as this particular portion, right? So yeah, so you end up with CO2 and H2O, which we discussed earlier on. Okay, and then the parts in the middle will actually give me ethane dioic acid, or what we call oxalic acid. So oxalic acid is the common name. So oxalic acid or ethane dioic acid is actually unstable in the presence of oxidation conditions. So it will be further oxidized to give you 2CO2. Why is it unstable? I can roughly explain, just very briefly, because CO is a very strong electron withdrawing group. Okay, so this electron withdrawing group, right, actually leads to the weakening of the CC single bond here. So this becomes a weak CC single bond. So that a weak bond is usually relatively reducing because the electrons tends to be lost to strong oxidizing condition or strong oxidizing agent. Yeah, and KMnO4 being a strong oxidizing agent is able to grab hold of that electron very quickly, and in the process, yeah, I'll generate CO2. Yeah, and therefore ethane dioic acid is oxidized from +3 oxidation state to +4. Okay, yeah. So yeah, it might be worth it might be worth remembering the unique case if you want to, but if not, then it doesn't really matter because you should be able to work out on your own if you are familiar with the chemistry of ethane dioic acid. Okay, yeah. So what's the usefulness of oxidative cleavage? Usually it's a useful tool to establish the location of CC double bond in a hydrocarbon or ring, and then you can actually use to distinguish between alkenes with compounds with terminal alkenes and those without, because CO2 is usually being released. Yeah, but of course the first point is actually the more important point which you might want to mention. But not to worry, a question will not be asked like that. I mean, we will not ask you the usefulness of oxidative cleavage usually. Okay, because this question again is not so crucial. Okay, but oxidative cleavage is usually important in structural elucidation kind of questions, which you will encounter in your alkenes tutorial. Okay, yeah. Okay, so yeah, gonna have an exercise 4.5 here. So we are going to try to draw out the product. Okay, so so there's some space here. So I'm just going to use all the space to illustrate. I might need to erase as and when necessary. Okay, so this particular alkene actually looks like this. So we have a alkene here, and then like this. Okay, so I'm going to in addition to what I've taught you earlier on, right, I think I'm going to show you a very unique, not unique, but a very systematic way of doing so that you will not miss out anything. That is numbering the carbon. Okay, so I'm going to number the carbon 1, 2, 3, 4, 5, 6. So there are 6 carbon in total. Okay, so the first thing I'm going to do is oxidative cleavage. I'm going to cleave the CC double bond, right? Okay, so you realize that I'm going to end up with this particular structure. Okay, so it's carbon 1 and 2 and 3. So carbon 1, 2, 3. Remember what I did earlier on? I'm supposed to draw out the double bond, right? Double bond O. Yeah. So this is a ketone, right? Okay, so if it's a ketone, we leave it as it is. okay, because it will be the product which we are going to draw. And then remember that carbon 6 essentially, if you draw out, it's actually a terminal alkene. Okay, so there is a terminal CH2 here. So in that case, for carbon 6, I'm going to end up with CO2, okay, and plus H2O. All right, yeah, okay. Then you might be wondering, where do I get the CO2 and H2O? Okay, so it's actually here. So it's actually over here. Yeah, so you're gonna end up with the CO2 and H2O. Okay, so this is the part which we are talking about. Okay, and then moving on to the next part. Okay, we're gonna have carbon 4 and 5, right? But in the above, carbon 4 and 5 is what we call the interesting exception. So remember, yeah, so I'm just going to number this as carbon 4 and 5. Okay, so if you're going to incorporate the double bond O in, you're going to realize that you're going to end up with a dialdehyde, and then of course what we call an ethane dialdehyde acid, right? And remember that this is a special case. Yeah, so because it's a special case, right, it will be further oxidized to give you CO2 and H2O. Yeah, so we're going to erase this whole thing. And then because it's CO2 and H2O, right? So I'm just going to redraw it a few times. So CO2, carbon 5, CO2, carbon 6, and then of course the H2O. Yeah, so altogether, I'm going to end up with 3 products. A ketone, in this case a propanone, 3 CO2 and 2 H2O. Okay, yeah. Okay, so the next thing I'm going to do is part B. So again, same thing, I'm going to number the carbon. Now, numbering carbon doesn't mean I have to number every single carbon. All I need to do is just to number the key carbon. So carbon 1, 2, 3, 4, 5, 6. Yeah, so again, for oxidative cleavage, I'm cleaving C1, C2 pi bond. Okay, so I'm going to end up with, again, if you follow what I said to you earlier on, you can simply just draw this out as it is. Okay, so this is the H, and then double bond O and double bond O. So we just need to ask ourselves one little question: is this aldehyde or ketone? So this portion is ketone, right? Yeah, so we'll just keep it as it is. And then this portion is actually an aldehyde, so it will probably not survive under strong oxidation condition. So because it will not survive, it will be further oxidized to give me carboxylic acid. Yeah, so you can draw this as the answer. Another reason why numbering carbon is good is because it helps you to keep track of the number of carbon you are drawing, because sometimes students will draw too many carbons, usually 1 extra carbon. Yeah, so there are 6 carbon in the ring. Yeah, so I did not draw extra carbon. Yeah, of course, if you are the type of students which wants your answer to be very nice looking, then you should be drawing it straight chain. So 2, 3, 4, 5, 6, 7. Yeah, so I will be drawing this as a straight chain, which looks like this. So this is 2, 3, 4, 5, 6, and then carbon number 1, and then OH. Yeah, so this will be the answer which I will draw if I want my structure to look nice. Okay, 4, 5, 6, 7. Sorry, not 7. Carbon number 1. Yeah. Okay, so I hope this numbering of carbon really helps a lot. And let me emphasize that if you don't know what to do, number your carbon first. Yeah, because once you number the carbon, the rest of the part is easy to be accomplished. Okay. Yeah, so I'm going to do the same thing. I'm going to number the carbon 1, 2, 3, 4, 5, 6. So again, oxidative cleavage. I'm going to cleave here and here. So yeah, I'm going to end up with 2 portions over here. Yeah, so for those of you who are already quick enough, you know that carbon number 2 has a H, carbon number 6 has a H, carbon number 5 has a H as well. Yeah, so without even going to further details, carbon number 2 will give me a carboxylic acid, and carbon number 6 will result in a carboxylic acid as well. Okay, and then for the top portion, carbon number 5 will result in a carboxylic acid, and then carbon number 3 will be a ketone. Okay, so if I'm just going to put in the numbers, this 1, 2, 6, and then 5, 4, 3. Yeah, you realize that it can be done quite quickly if you are very sure about what's going on. Yeah, if you're not sure about what's going on, sometimes it's difficult to actually accomplish the task. Okay, yeah. And then with this complicated looking molecule, sometimes you realize that if I number the carbon, it will take a long time. Yeah, well, I mean, I think you should number. Yeah, but of course, if you are able to maintain your poise, actually sometimes you do not really need to number the carbon, and you already can end up with the answers. Okay, so what I can illustrate here would be, I'm just going to draw this out in the way it should, and then double bond. Okay, and then double bond. Wait, sorry, I thought I should draw this out separately. Okay, like this, and then like this, and then the double bond. Okay, and then the double bond, and then ketone here, and then a CC double bond. Okay, so if you recall what I did earlier on, right, basically erasing actually helps a lot. So all I need to do is I erased, and I erased. And then after that, I'm just going to replace them with a double bond O. Double bond O, double bond O, double bond O, and then double bond O, and then of course it's OH. Okay, double bond O, OH, double bond O, OH, double bond O, OH. Okay, and then double bond O and OH, and then the final part is a CO2. And that's it. Okay, so this will be the answer which you're going to present. Present to the examiner. Of course, it looks ugly. Yeah, then if you are the type that wants it to be neat, so you can draw it nicely. Like this is propanone, so I'm going to draw it like this. And then this whole chunk it looks really long, but if you look at it slowly, so that's carbon 1, 2, 3, 4, 5, 6, 7, and then 8, 9. Okay, so if I draw it nicely, it'll be 1, 2, double bond O, and then 3, 4, double bond O, and then 5, 6, 7, and then 8 will be double bond O and then OH, and then 9 will be double bond O and then OH. Yeah, so it can be drawn nicely if you want to. Okay, and then for the other one will be same thing, 1, 2, 3, 4, 5, 6. Okay, so again, you'll be like this, okay, and then like this, and then like this. Yeah, okay, and then plus CO2. Yeah, so this will be the nicer version of the answers, if you wish to. But of course, if you are running short of time in the exam, just whack and then just erase and then just write in the answer. I think that will be fine. Okay, and then of course, for planning wise, you need to learn how to write out the generic procedure for distinguishing tests for alkenes. Okay, and then usually for alkenes, we will use acidified potassium permanganate, which will actually result in oxidative cleavage. Okay, but you need to take note that the amount of acidified KMnO4 you are going to add, right, should be 2 to 3 drops. You shouldn't add too much. The reason is, if you add too much, right, then the KMnO4 become the excess reagent. So the solution will not change color. It will remain as purple. So this is often a mistake which students make during exams. During practical exams. Yeah. So when you're supposed to add 1 or 2 drops, make sure you add 1 or 2 drops, not too many drops. Okay. But usually we do not recommend students to use potassium permanganate as a distinguishing test. The reason is potassium permanganate, being a very strong oxidizing agent, can undergo many other forms of oxidation, which you will learn later on. So bromine water is actually the top choice. But again, bromine water add drop wise, not too many drops. Okay, and then we have exercise 4.6. Why should KMnO4 be added drop wise? I think I've explained. If you add excess, solution will remain purple because KMnO4 becomes an excess reactant. Yeah, and you don't want that to happen. Okay, so drop wise is a must. Okay, actually same reasoning goes for bromine water. Okay, then for bromine water, if you add too much in excess, the solution will remain as yellow orange. You will not be able to observe the decolorization. Yeah, And I hope you also remember that in your practicals, please follow instructions carefully. When they ask you to add dropwise, make sure you add dropwise. All right, okay. And then the summary of the reactions here, I'll leave it to you to fill in the boxes, okay, so as to familiarize yourself with the necessary conditions in order to get the addition products, okay, either the addition product or the oxidative cleavage products for that matter, okay. And then earlier on I mentioned that we have an appendix here showcasing to you the electrophilic addition of water or steam in the presence of concentrated sulfuric acid. So the first step usually involves the electrophilic addition of H2SO4, okay, and then same case, you generate a carbocation, and then your HSO4 minus, okay, being a weak nucleophile will then attack the electron deficient carbon, and you will generate this interesting looking hydrogen sulfate species, which can be easily hydrolyzed in the presence of either alcohols or water. So in the presence of water, this CS, or in this case the CO bond, is weak because of the presence of sulfur, and it will be hydrolyzed relatively quickly, and then you will actually generate the alcohol in no time, okay. But take note that remember that in the hydration of alkene using concentrated sulfuric acid, the condition is it must be done in cold condition. So this is actually the first reagents being added. Yeah, so in a cold condition, you generate this hydrogen sulfate as a product. And then later on, when you pour cold water inside, then this bond will be hydrolyzed, and in the process give you the relevant alcohols. Okay, yeah, so and that's the end of the alkenes lecture. Yeah, and that will be it for this current topic. And then the next topic will be on arenes, and then do look out for the next video.